Good day. Welcome to the second part of our discussion video on surface integrals of vector fields. In the first part, we tackled the first four items here, where items 1 and 2 dealt with the flux of a vector field across a parametric surface, while 3 and 4 dealt with Cartesian surfaces. Here, note that the first four items all have positive orientation. So for items 5, 6, and 7, we will be considering variations to this problem of solving for the flux. All right, let's start. Let's consider the vector field F equal to x squared, x plus e to the y, and -1, acting across the rectangle x between 0 and 2, z between 0 and 4, in the plane y equals -1, but this time the surface is oriented in the positive y direction. Okay, so let's take a look at how these objects will alter our solution. Okay, first, we describe the surface S. Usually the format is z equal to some function of x and y, no? But here, note that we only have y equals -1 in this case. So we will be altering the surface by using a function of x and z. So we will have y equal to g of x and z, equal in this case to -1. Okay? So, ano ang magiging effect nito doon sa normal vector? In the previous four items, we had something, something, and 1, or -1, depende doon sa orientation. Here, since we have a surface oriented in the positive y direction now, we will need a normal vector which will reflect this orientation. Okay? So, since y direction ang orientation natin, the y component of this normal vector must be fixed. It must be constant. Okay? And since we are oriented in the positive direction, it should be +1. Okay, so that's your second component. Now, as for your first and third components, sila ngayon yung usual na g sub x at g sub y, but this time, they will be of the form -g sub x and -g sub z. Okay? If we're not convinced with that explanation, then we could think of this vector as the gradient of the surface with equation or function y minus g of x and z. So y minus g of x and z has this value or vector for the gradient. Okay? So that is how we got that normal vector, which in this case, if we plug in g sub x and g sub z, well, they are both 0. So we will get this normal vector, 0, 1, 0. Okay? And that will be the normal vector for your flux. So the usual surface integral will be converted into, this time, magiging, instead of x, y, and function of x, y, it's going to be x, g of x and z, replacing y, and then z. Then dot the normal vector that we computed earlier. Okay? So let's fill in the blanks. Here, g of x, z is equal to 1, or -1 rather. So, ang effect lang niya, itong y lang na to, ang mapapalitan ng -1. So there's f dot n, which is 0, 1, 0. Okay? And this dot product will be evaluated over the region indicated here. Okay? So we have x from 0 to 2 and y from, or sorry, z from 0 to 4. Okay, so we switched already to the iterated version, no, of the double integral with integrand 0 plus x e to the -1 plus 0. with dA being dz dx. Okay. Now look, here we have an integrand independent of z. So we can do your splitting, again, upon checking na constant yung bounds. So we have the flux equal now to an integral from 0 to 4 times an integral from 0 to 2 for x of x plus e to the negative 1. Okay? And so we can do the integration. The first one is equal to 4. The second one is x squared over 2 plus x over e from x equals 2 to x equals 0. And we can solve for the values there. That's 4 times, well, at x equals 2, we have 2 plus 2 over e. And then at x equals 0, 0 lang lahat yan. So the final answer will be 8 plus 8 over e units for the flux of F across S. Okay. Take note, this solution was made possible by adjusting your normal vector, which should follow your surface and its orientation. So here, the surface is oriented in the positive y direction. That is why your normal vector earlier had a 1, positive 1, in the second component. Okay. So that is item number 1, or number 5 rather. Okay, let's try item number 6 now. We have this vector field xyz across the portion of this sphere where x is greater than or equal to 0. Okay, here take note, x yung non-negative, hindi z, hindi y. Okay, so we have this portion inside this cylinder, y squared plus z squared equals 1. And this time we are orienting your surface in the negative x direction. Okay. O, iba to, no? Negative x. So, what do we do? First, we set a surface, no? An equation or a function for the surface, which will be from this part, since x yung focus na non-negative, it would make sense if we solve for x here, sa equation of sphere. So we have x as a function of the other two variables, y and z, like this. Okay? So dyan manggagaling yung normal vector later. But first we check kung ano yung region of integration. Okay, let's try that. It's the portion, the surface is the portion of this guy inside the cylinder. Na kapag pinroject natin sa YZ plane, doon mas madali mag-project, will be precisely your circle in the YZ plane of radius 1. Center origin, okay? So we will be using that later for your integration. Yeah, there's a bit of a hint there. Maybe we could use polar form. And now for the normal vector. Okay, ito na. The normal vector, ito ang normal vector natin, oriented sa negative x direction, following yung orientation ng surface. So, just like earlier, we could fix the x component, yun, kung saan nakadirect yung surface, x direction. So we could fix x there and make it negative 1. Negative x. Kaya may negative 1 dito. Okay? And for the other two components, they should have different signs from this fixed component here, which is why we have g sub y and g sub z. Okay? Well, again, if you don't like that explanation, you could think of it as the gradient of this time, since negative, gusto natin negative x. So gusto natin magkaroon ng negative x from this equation here. So we could consider the function g of y and z minus x. Minus x, okay? So g of yz minus x, tapos yung gradient niya will be precisely this vector. Okay, so we could do that. Okay. Anyway, once we've settled that variation to your normal vector, we can rewrite the expressions -1, that's g sub y, and g sub z. Okay, so yan ang papasok doon sa surface integral natin for the flux, f dot n, like this. And now, yung usual replacement natin na z dapat, ngayon, x yung papalitan natin. So we will have f of x, which is the square root, and then y and then z, dot the normal vector that we established earlier. Okay, let's evaluate f first at these inputs. It's going to be that. X, y, z lang naman siya. So there. Dot that vector, this guy here. No? And when we simplify this dot product, please verify, I will leave it to you, na ito ang itsura niya. -4 over square root of 4 minus y squared minus z squared, dA, double integration over the region D. Ayan. Okay, so earlier we noted that the region D is this interior nito. Yung interior ng unit circle. Okay? So that would be easier to deal with in polar coordinates, where we have the standard, no? Standard bounds u from, or theta, sorry, from 0 to 2 pi, and r from 0 to 1. Again, since we have y squared plus z squared equals 1. Okay? So now, we can solve for the flux. Well, we just group the negative sign dun sa baba, yan siya. Now, if we want to convert to polar form, then we have these bounds, 0 to 2 pi and 0 to 1 for theta and r respectively. And then, okay, itong y squared plus z squared na ito, para siyang x squared plus y squared sa usual setting. So ito, pwede natin siyang palitan ng r squared. Okay? Since again, kamukha siya ni x squared plus y squared equals 1 in the usual setting. And then we have -4. And for dA, it's going to be the usual r dr d theta. Okay? Yan. So hopefully we got to this point, which is, ayan, yung integrand na to is independent of theta, so we can do the split. Integral for theta from 0 to 2 pi, and integral for r, like this. Okay? Now the first integral, well, that's going to be 2 pi. We will do that later. Let's focus now on the second one. Maybe we could use some substitution here. Huh? In particular, we could let u be 4 minus r squared so that its derivative is -2r dr. Okay? So now we can evaluate these integrals separately. May 2 pi dito. And then for this second one, when r is equal to 0, u is going to be 4. And when r is 1, u is going to be 3. Giving us the following bounds in u. Careful, in u ito, hindi in r. Kasi nagsasubstitute na tayo, no? So u from 4 to 3. And then, well, the denominator is square root of u. And as for the numerator, together with the dr, it's essentially 2 du. Okay? So that's 2u to the -1/2 with antiderivative for u to the 1/2, which we evaluate from 3 to 4. Okay? And now we could just solve for the final value. Well, we could match or merge the 2 pi and the 4. That's 8 pi. and then square root of 3 minus square root of 4. So that will give us the final value of the flux of F across this surface, 8 pi square root of 3 minus 16 pi units. Okay, so again, this computation was made possible by noting that your normal vector, since your surface is oriented in the negative x direction, must be of the form -1 for x, and then g sub y, g sub z. All right? Hopefully that's clear why we took this n in exercise 6. Okay, that's exercise 6. One last. Ito na. Konting push, guys. Okay, so we have here the vector field 0, z, and -y acting across the surface S, consisting of two parts. The paraboloid z equals x squared plus y squared, where z is between 0 and 1, and the disk on the plane z equals 1, which is basically the interior of a circle radius 1. Now, we note that the entire surface is oriented outward. Okay, so let's think about it. Oriented outward. Hindi siya upward, downward, or anything, ano? Outward. So let's break it down later. But for now, let's look at the surface S. Ayan, may paraboloid, tapos may disk. Parang nilagyan natin ng tsokolate yung paraboloid. But the point is, this surface is defined using two separate surfaces, the paraboloid and the disk. So it would make sense for us if we consider the flux of F across S by splitting it into two. Bale, may flux yung paraboloid, tapos may flux dun sa disk. Okay? To shorten our words here a bit, let's call S1 your paraboloid and the disk S2. Okay? So that at the end of this solution, ang mangyayari is that the flux of F across S, yung buo, is going to be the flux of F across the paraboloid plus the flux of F across the disk. Okay? So, yung flux ni F sa paraboloid tsaka sa disk, pagsasamahin natin. Okay? So we will have two computations for flux. First, let's consider the paraboloid. Okay? So F has a flux across that surface. Let's call it F1. Now, we take note, oriented outward yung surface. So, in the case of the paraboloid here, when we say it's oriented outward, then we should have some sense na yung normal vectors nito, palabas, pag ganito. So in terms of their z components, we will look here at the z components, no, as guided by your equations, z equals. Okay? So yung z component nila parang pababa, no? So it must hint at your normal vectors pointing downward. And we attach some vectors there to show our point na kapag oriented outward yung surface, in the case of the paraboloid, pointing downward yung n. Okay, so we will be using a variation of your normal vector for a negative orientation. Tama? Pag downward, negative. Okay? So now, if we take the surface and its equation z equals g of xy equal to x squared plus y squared, then we have the following computation for the flux. So, diretso na natin. Surface integral of f dot n which is the double integral of x, y, and here it's the default na, no? X, y, z. Where z is x squared plus y squared. Dot, eto na. Ano yung normal vector? Ano yung form? It should be downward sa z. So, ang z component ay -1. And then for the other two components, they should be positive g sub x, positive g sub y. Okay? Which we will take the dot product with f and then double integral over the region D. Okay. Now f here, we take its vector form, that's 0, x squared plus y squared, and then -y. Again, z there is x squared plus y squared. Dot, g sub x is 2x, g sub y is 2y from here. Excuse me. So we have that. And when we evaluate that dot product, we get this one. Hindi na natin i-expand, ano? Let's just keep the x squared plus y squared there. Para may hint tayo na baka mag-polar. Kasi, note that, itong paraboloid na to, if we project it onto the xy plane, we essentially get yung parang pang-cap niya yung disk. Yung x squared plus y squared less than equal to 1. So, the region D is actually the unit disk. Okay? So we have the usual bounds, theta from 0 to 2 pi in polar, r from 0 to 1. Okay. So that allows us to write your flux for F1 as an integral from 0 to 2 pi, integral from 0 to 1 of, okay, 2y times x squared plus y squared. In polar form, that will be 2r sine theta times r squared. Okay? And then may karugtong siyang plus y kanina, where y is r sine theta, and we have dA, r dr d theta. Okay? And now, okay, can we do the trick from earlier na magsisplit? Well, we could take out a sine theta from both terms, and the bounds are constant. So pwede, no? Pwede. Let's try that. So we have the integral from 0 to 2 pi of sine theta. And then the rest of the terms with the r, that's 2r cubed plus r, all multiplied with r, will give us this second integral. And ito na. This first integral here, it's going to be negative cos theta from 2 pi to 0. Pero cos theta it has a period of 2 pi, no? So cosine of 0 is equal to cosine of 2 pi. So in effect, magiging 0 lang to. So that's going to be 0 times something. Well, that will be 0 na lang. Okay? Notice we did not bother evaluating this integral because ang katabi niya 0 naman. Okay? So that's the flux of F across S1. 0 units. Okay, that's good. Okay lang yan. Right, so that's F1. What about the surface S2, yung disk? Ano yung flux ni F dyan? Okay, so again, for brevity, let's call it F2. The flux of F across S2. Okay. Now, let's consider kung ano yung equation which will serve as your g of xy in this case, no? We have the following equation, z equal to 1. Kasi nasa z equals 1 siya, no? So we will take this as your g of xy. Okay, question. Ano ang itsura ng normal vectors kay S2? With the knowledge na S is oriented outward? Okay, the answer will be, since oriented outward, palabas yung vectors. So in terms of S2, the vectors will be pointing upward. Yeah, we put some sample vectors there. But the point is they are all pointing upward. Okay. So we will be using here the usual version of your normal vector. Yung minus g sub x minus g sub y, and then 1. Okay, 1 on the third component, again, indicating upward orientation along z. Okay. Game. So we now have the necessary details for your surface integral for F2, where we have the double integral of x, y, and z, but z is 1. Okay. Dot, again, the n here must have positive 1 for the third component, with the other two being negative g sub x and negative g sub y. Okay. So let's get those two vectors now. We have 0, z is 1, and negative y, dot, the partials of z here are both 0. So 0, 0, 1 lang yan. And in the end, well, we get a double integral of negative y na lang. Okay, so let's do that double integration over the same region D. Take note. So same region D lang yan. So we have the same bounds, 0 to 2 pi, 0 to 1 of negative r sine theta dA, r dr d theta. And like earlier, so F1, we can split this integral. Sine theta from 0 to 2 pi, negative r squared from 0 to 1. Oh, eto na naman. Ayan na naman siya. Sine theta from 0 to 2 pi, we noted earlier that it's just 0. Whoop. F2 is also 0. F1 earlier is 0. So, eto na. To conclude exercise 7, we take the flux of F across S to be the sum of F1 and F2, which is 0. Yeah. So the flux of F across the entire surface is 0. Yeah. So notice we did the entire example using surface integrals, no? Na convert using double integrals. In a later lecture, we will be doing a simpler solution, or we will be encountering a simpler way of doing this example using what we call Gauss's divergence theorem. Okay? And that's it for this discussion video on surface integrals of vector fields. Should you want more examples, you may consult the module or online references other than this one. All right, and that's it. Thank you for watching this video, and as always, please stay safe.